Okay, so here's another round thing rolling down the hill. This is, the third or fourth time we've done this. We've done the ring rolling down the hill, the bowling ball rolling down the ice-covered roof, and I think we did some kind of sphere rolling down the hill. So now we have a barrel rolling down the hill. So let's do this. There's a little twist to this problem. There's all in variables. And it's asking for the angle where it's just about to slip. And so what that means, if it's just about to slip but it's not slipping, you have A equals R alpha because it's not slipping. And because it's just about to slip, you do have the friction force equal to mu n. So you have both things given. And in this case, you're going to use that information to solve for theta. Usually you're given theta, and one of these two things are true, either it's slipping or not. So this is the perfect theta. So if I were to give you a problem where I set the theta accidentally to this perfect theta, it will be very confusing. Or actually, you could get it right whichever way you chose, if it's slipping or not slipping. But I won't do that. Okay, so let's see if we can solve this. So in this case, here's the free body diagram. So we know we have the W, the normal, and the friction force, and there's MA going down the hill and I alpha spinning. And one of the first things we're going to do is we got to break that W into the part that's going down into the ground and the part that's going down the slope. And that will be W cosine theta. In this case, going down into the ground, and pushing it downhill will be W sine theta. Okay, so I'm going to take X and Y down the hill and normal to the hill, respectively. And so let's do the Y forces so we can solve for the normal. You have the normal going straight up. And then you have W cosine theta pointing down, so N is W cosine theta. We'll take the X components going down. Driving it downhill is W sine theta. Going back up is a friction force, but because it's about to slip, we know it's mu times N. And then it equal MA. And in this case, because it's about to slip, but not quite slipping, we know that A is R alpha. So there's our second equation. And finally, we'll take moments about the center of gravity, so we don't have to deal with the weight. And so you have the friction force times R, but again, the friction force is mu times N equals I alpha. And it says that the radius of gyration is K0, so I is K0 squared times M, and again, times alpha. So here we are. We have three equations. All you have to do is solve for theta. And so as I did this, the first thing I did was I took this equation here and substitute N into the other two equations. Okay, so you can see that here. So here's equation 2 with N eliminated, and here's equation 3 with N eliminated. So then we're trying to solve for theta. Okay. So we need to solve for theta, but the problem is we don't know what this alpha is. So there's this other unknown alpha. So what we're going to have to do is solve for alpha and plug it into equation 2. And I was just being a little clever with the algebra there. I took this equation here and I solved it for R alpha. And then I took that R alpha and then put it back into equation 2. And that ended up with this. You see the G's canceled out. You can factor out, you put all the sine theta on one side, the cosine theta on the other side. And then you divide by cosine theta and you get tangent theta. Now, just a comment about the solution. In statics, if you remember, for it to start slipping, tangent theta had to be mu, but because of this rolling, you have this extra R divided by the radius of gyration squared onto that, so it has to be a little steeper to make it slip and roll. But that's that problem. So we've done these kinds of problems so much, I'm going to give them their own name. Yartdah. Yet another round thing rolling down a hill. Okay.